third part of this lecture. Here, we are going to define a suitable value of R and show that the two claimed bounds are correct. For the first one, recall that this big Y is a Poisson random variable with parameter m. And then we want to show that the chance of Y deviating from the mean value by this chosen R will be equal to 0 when m is very, very large. Recall also a little bit that when Y is a Poisson random variable, in some sense, it is similar to a binomial random variable, and its distribution is concentrated around the mean. And for this particular case, we are going to set R to be the square root of 2m log m. Once we have set R to be this one, so the next one we are going to analyze what is the probability of this term. So for the probability of this term that we want to find, it is actually divided into two cases. One is when Y is very large, greater than m plus R, and the other case is Y is very small, less than m minus R. And then these two fits for something that we have already proven before, the Chernoff bounds. This is the right tail, and this is the left tail. And then we are going to show that for each of these terms, this is the first term, this is the second term, the value of this will be 0 as n or m tends to infinity. So m is the value here that we see, and recall that the value of n and m are related in the sense that m is equal to n log n plus cn. Okay, now for the first term, this is a Chernoff bound for the right tail. So we copy this from something that we have studied before, and doing some cancellation because we now have the parameter of the Poisson random variable to be m. So we have this formula. So e to the power minus m and e to the power m here cancels. So after simplification, we get something like this. So the e term will be gone. And since this term is rather difficult to see, so we replace it into the exponential form. So this is going to be e to the power, this is the power, r, and then you have this one, m plus r log m, and then minus m plus r log m plus r. So in that case, after simplification, this is minus of m plus r multiplied by log of 1 plus r over m. Now we are going to use the relationship that log of 1 plus z is greater than or equal to z minus z squared over 2. So this is coming from the Taylor's expansion. So you expand the log of 1 plus z for a few terms, and then in the end, you will see that log of 1 plus z is equal to z minus z squared over 2 plus some error term. So plus some positive error term. So in that case, then we have this relationship. Based on this formula, we replace the term log of 1 plus r over m into r over m minus the square of this term divided by 2. So this is r squared over 2m squared. Okay, so we copied this formula from the previous page, and now we are going to do some simplification. So first of all, this r squared, so because r is equal to the square root of 2m log m, r squared is equal to 2m times log m. So 2m and 2m squared, you can cancel it so that in the end you get log m divided by m. Okay, now for the next part, then first of all we see there is an r here, and then let's process this m part. So we have minus m times r over m, so the r term will be cancelled, and then we have minus m times minus of log m over m, so we get log of m. And then we process the term, this r here, the minus r term here. Minus r times r over m is minus of r squared over m, so r squared over m, you get this one over m, so this is 2 log m. And minus r times minus log m over m, it is plus something, but then we will see that this term is of little of log of m. So once you see that in the exponent part, it is log m minus 2 log m plus a very, very little term. So it is going to be close to minus of log m. So exponent of minus of log m is 1 over m. So it is going to be equal to 0 as m tends to infinity. So this is the bound for the right tail. So let's see the left tail. So we do exactly the same thing as before. So but this time we copy the Chernoff bounds for the left tail. And then after cancellation, we will see exactly the same way as we cancel terms, so that we will get log m minus 2 log m. And then here, this is another further minus of a very small term, little of log m. So after cancellation or after simplification, this one is equal to 1 over m, or very close to 1 over m. So it is also equal to 0 as m tends to infinity. So now we have proven the first term and the second term are both close to, or is going to be equal to 0 as n tends to infinity. So we have proven our first bound. Okay, now let us move on for the second bound. So at this time, the r value is already fixed to be square root of 2m log m. And we want to show that the probability of having no empty bins, given this information, y is close to the mean, will be the same as the probability of having no empty bins when y is exactly the same as the mean value m. Recall once again that it is normally difficult to compare conditional probabilities. But thanks to the relationship between conditioned Poisson case and the exact case, then this is going to be able to do so. Now to prove that this one is equal to this one as n tends to infinity, we are going to show that the difference of these two terms, so the absolute difference of these two terms, is going to be equal to 0 as n tends to infinity. Okay, so before we move on, let us first observe this term, the probability of having no empty bins, given that y is equal to k. Now this term is a conditioned Poisson. Conditioned with the total number of balls is exactly k. So as we have proven before, this is the same as the probability of having no empty bins in the exact case when exactly k balls are thrown. Because we know that as more and more balls are thrown, then we will see fewer and fewer empty bins. So the chance of having no empty bins will then increase as k increase. So in that case, the probability of no empty bins given y is equal to k will be increasing in k. So this is an important fact that we are going to rely on. Okay, next, let us analyze this term. Now for this term, we can compute it exactly from the definition. This is probability of a certain event given another event. So this is equal to the probability of the first event intersect the second event divided by the probability of the second event. Now, let us take a look at the denominator first. So the denominator is about the probability of y close to the mean. So by law of total probabilities, so we will see that this is the summation of all the cases of y is equal to k, where this k value is between m minus r and m plus r. So we will add all things up, so we will get this one. Now for the first part, we can also see that we can use total probabilities here to analyze this probability. So let's see this term first. Probability of y is equal to k multiplied by probability of NE given y is equal to k. So these two, when we multiply them together, this is exactly the probability of no empty bins intersect y is equal to k. Now in order to find out this probability, we just need to sum up all the cases of k where k is equal to m minus r up to m plus r. So if you look at this term, this part is the same as this part, but then we cannot cancel them because the right hand side, this part, is not a constant. If it is a constant, that would be nice. Then let's see the relationship. Here, we claim that the probability of NE given y is equal to n minus r is going to be a lower bound for the desired term that we compute in the previous page, and then this term is further smaller than or equal to the probability of no empty bins given y is equal to n plus r. The reason is when we replace this one by y is equal to n plus r, then we will see that all the terms here, y is equal to k, will be less than or equal to the k-square probability of NE given y is equal to n plus r. So if we replace all these terms of different k by the same term, y is equal to n plus r, then we get an upper bound. So if we replace it by that particular value, then this part and this part can be cancelled. So we will see that this probability will be less than or equal to the probability of no empty bins given y is equal to n plus r. So we will get this one. We will get the relationship of this one less than or equal to this one. And similarly, if we replace this term by the smallest possible value here, which is probability of no empty bins given y is equal to n minus r, we will get a lower bound of this one. So in that case, the probability of this term y is close to the mean value is bounded by these two cases. Okay? Now on the other hand, the probability of no empty bins given y is equal to m is also bounded by these two. It is because we have just mentioned that this probability function is increasing in the value of this part. So in that case, we also have this bound. And recall what we want to find. We want to find the absolute value of the difference. So this is the difference of these two terms, right? Each of these terms, so this term that we want to find and this term that we want to find, right? So we want to find the difference of them. So each of these terms are bounded by this one and this one. So the difference or the distance cannot be more than the distance of this term and this term. Okay? So this is what we want to claim. So the absolute value of this one that we want to find is less than or equal to the probability of having no empty bins given y is equal to n plus r, and then minus the probability of having no empty bins given y is equal to n minus r. Okay. Now, at this point, we are going to use the relationship of conditioned Poisson is equal to exact again. So the first probability here corresponds to the case where when we are throwing exactly n plus r balls, there are no empty bins. And then this term corresponds to the case where we are throwing n minus r balls, such in the exact case, such that after throwing these balls, there are no empty bins. So the difference of these two probabilities can be interpreted as we look at the exact case and find out what is the probability of having no empty bins. But for the first one, we can throw n plus r balls, and for the second one, we can only throw n minus r balls. So this probability difference is equal to, so this is another way of saying that it is equal to, so the difference itself is equal to when n minus r balls are thrown, there are still some empty bin, but then when n plus r balls are thrown, then there will be no empty bins. So that's why we have this probability minus the probability of having no empty bins when n minus r balls are thrown. So minus that one means that, so the difference comes from, at that point, after n minus r balls are thrown, we still have some empty bin. Okay. Now, in this case where this probability difference happens, what we see here is that when two r balls are thrown further, all the existing empty bins have to become non-empty. So we will see that the above probability difference must be smaller than or equal to this simpler case, that when two R balls are thrown, one of the empty bin, some empty bin becomes non-empty. Notice that this is much easier to happen than all empty bins become non-empty. And for this one, when two R balls are thrown, each ball, you can make the corresponding empty bin to become non-empty with probability 1 over n. So by using union bound, this probability is less than or equal to 2R divided by n. But if you recall that R is equal to this value, and then m is roughly n log n, so in that case, R is of the order of something like square root of n polylog n, so it is much smaller than n. So because it's of square root of n polylog n, and here it is a full n. So as n tends to infinity, this term becomes 0. So what does that mean? So we have proven the second bound, because we have proven that the absolute difference of these two terms is going to be equal to 0 as n tends to infinity. That's all for this part. Thank you.